Okay, so back here continuing to talk about fluid mechanics and hydraulics and pumping. And in the last video we went through and introduced this idea of a pump curve that's shown here. The idea is that we're trying to get energy from a rotating shaft, and we're going to use that to create a pressure increase inside of a fluid through a pump. And the pump curve tells us the relationship between the amount of energy we can get out of the pump into the fluid at different flow rates. So the faster water flows through the pump, the more energy losses there have, which means there's less energy the pump can actually give to the fluid to help make it move. So this pump curve slopes down. Pump curve is also going to tell us the efficiency. So at really high flow rates or really low flow rates, a pump is not going to be very efficient. It's going to have a point where it's most efficient. And then there's going to be a power requirement that's going to change as you increase the flow rate. So I want to talk here in this video how we can use that to help analyze the flow rate that you would get for a given pump inside of a pipeline. So pump and pipeline analysis. When pumping water in a hydraulic system, it's very complicated, so we have to think about the friction losses in the pipe. We have to think about minor losses in the pipeline. We have to think about other kinds of energy transfer that might be happening, like elevation changes. We need to think about the costs of the energy, the amount of water that we need, the pressure that we need at the delivery point. There's a lot of factors that we have to consider. And so that's why we have to know how to predict the flow rate, all these different things at different flow rates, so that we can understand, if I buy this pump and put it in this particular pipeline, what is going to happen. So thankfully people have figured out how to do this. So the operational performance of a given pump is going to depend on the pump and the system. Okay, so this is the key idea, is we have one curve that's information about the pump curve, and then we have to also think about what's going to happen in that particular system. And so we're going to go through an example of that here. So to determine the operational characteristics of a pump, we have what is called a system curve. A system curve is also required. The system curve will generally look something like this, and it's going to be a little bit more complicated than this, but in a simplistic way, we can think about it as having just two components, some constant A plus some other constant B times Q squared. So where Q is the flow rate, and then this is the system head. And so this big H system is the energy that it takes to move fluid at a given flow rate through a pipeline. H pump is the energy I get from a pump at a given flow rate. So the energy that I get from the pump has to equal the energy that gets used up in the pipeline. That's the main idea. Okay, the first term here, the constant A, represents what we might call the static head. That's the energy needed to lift the water. So if we're pumping water, trying to get it from one place to another, it might be going downhill. So we might not actually have to lift the water at all, but you might still need to pump it to get enough flow through that particular pipeline. But a lot of times we are pumping it uphill because we'd like to use gravity and not have to pay for energy. But most of the time when we're going uphill, we're going to have to, or oftentimes we want to go uphill, so we're going to need to use a pump to make that happen. So it's got this static head. Okay, that's a constant. The amount of lift you need doesn't matter how much flow there is, it's still going to have to lift however much it needs to lift. And then the second term we might call the dynamic head, and that represents the friction and minor losses. Then those depend on the flow rate, so that's why there's a constant times Q squared. The operation of the combined pump within a given system, a given pipeline, can be determined by plotting the system curve, the energy consumption from static head and dynamic head, on the same graph as the pump energy supply that we're getting from the pump. And where they intersect is what's going to be the reality of that situation, and we call that the operating point. Okay, operating point. Typically, we get this pump curve from the manufacturer. So somebody makes a pump and they're going to give us this information. And they're typically going to give you a curve like this. They're not going to give you formulas. So we have to do this. So this is typically done graphically. In theory, you could like fit a curve to these different things, and then you could do it without having to plot it. I would kind of like that idea if you could, if you could do it. But we're going to look at the traditional way where we are plotting the system curve on here and using that to figure out what flow we would get. Okay, so remember, this is the energy supplied by the pump, and we're going to come up with a new equation, A plus BQ squared. So here's Q, and we're going to plot it on here, and it's A plus BQ squared, which means that Q is 0. It's going to have some value representing the height that we lift the water, and then the actual energy is going to go up from there as we have more and more friction losses, and then we get less and less energy out of the pump. So wherever those intersect, that's the operating point. That's going to tell us the flow rate down here. That's going to tell us the head that actually gets supplied by the pump and consumed in the pipeline, and then we can read off the efficiency and the power at that flow rate. So easiest way to understand this is to do an example. So here we're told that an engineer has been asked to investigate the performance of a pump to lift water 20 meters in a 1,000 meter long 30 centimeter diameter pipe with a friction factor of 0.02. Now, of course, we're typically not told what the friction factor is, since this example is focused on helping you understand how to do pumps. We're just saying it's 0.02. But in a more realistic problem, you'd have to look up the relative roughness, and you'd use the Moody chart, or you use the Swami-Jain equation to calculate friction losses. But so here, it's a little simpler because we're just told it's 0.02. Manufacturers provided the following data for the pump. So this is the pump curve, and then what flow rate can be delivered by this pump in this pipeline. And we're also told that the efficiency is going to be 80%. Now, in reality, the efficiency depends on the flow rate. So this is another simplistic thing in this one, but just to get you thinking about the ideas and to get us through an example, we're just saying it's going to be 80%. So how much power is going to be needed then at that flow rate? Okay, so we're told here that the length of the pipeline is 1,000 meters. The diameter of the pipeline is 30 centimeters, which is 0.3 meters. The friction factor is 0.02. We don't have to calculate roughness, don't have to use the Moody chart. We're going to need the acceleration due to gravity, 9.81 meters per second squared. Okay, so this is information that was given to us in the problem, and then we have our pump characteristics. This has nothing to do with the pipeline. So remember, the pump has its characteristics, the pipeline has its characteristics. The pipeline is energy losses from friction, exactly 100% the same thing we've done in the past. But this is the new thing here with the pump curve. So let's draw a little diagram to help us think about how to do this. So we got water here in our starting reservoir, and then we've got it going into this other reservoir, and this is just like what you might see in the real world here. If you have let's say you have a drinking water plant, the clean drinking water comes here, and then we pump it up to a water tower at some level, and we need a pipeline to do that. And so we've got this pipe that goes out here, and then it has a pump that it connects to that sends it up here into the tower or wherever we're going. Okay, and we're told the difference in height here is 20 meters. Delta Z is 20 meters. Okay, that's the difference in height there. Okay, and yeah, information about the pump is given here. And so how are we going to analyze this thing? So we're going to use an energy balance just like we did before. So we have 0.1 here and 0.2 here that I'm going to use for my energy balance. I'm choosing those points because they make things easier. So our energy balance, some people would call it Bernoulli's equation. It's not Bernoulli's equation though, because Bernoulli's equation is for frictionless flow, and this has friction. So technically not the same thing, but P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2. And so this would be for inviscid flow, but so the pump is adding energy in. So the energy here has to equal the energy there plus whatever losses there were in between. Okay, so plus HL, the losses, and then over here we've got to add plus H pump. So the pump is going to provide us the energy to overcome the change in elevation and the friction losses. Okay, so it's 0.1 plus whatever inputs we get from pumps equals 0.2 plus whatever losses we have from friction. That's going to be the general formula for our energy balance when we have pumps. So this is the new part here. Okay. And so by cleverly choosing this point here and this point there, then the velocities are going to be negligible and the pressure is going to be atmospheric at both places. So we just get that H pump has to equal to Z2 minus Z1 plus HL. And so if I call that Z2 minus Z1 is my delta Z. So Z2 being higher, it's going to be a positive 20. That's our static head. And then our friction losses are going to be from the Darcy-Weisbach equation, FL over D V squared over 2G. And then we can also write rewrite that in terms of Q delta Z plus 8FL over pi squared G D to the fifth times Q squared. Okay, and so all these things here are given constants. Q is what we don't know. We know delta Z, we know all these things, and we don't know the pump head, and we don't know the flow rate. These are the things we want to know. So that's why we're doing the analysis. So you'll notice here this is like A plus BQ squared, just like we talked about before. And so we're going to call that H system. So H system is the right-hand side here. This is the energy requirements, and then H pump is equal to the pump curve. All right. So we got this from our energy balance. We don't know what H pump is. We can't just say this isn't a constant. You can't think of it as a constant, and neither is Q. This is really like two equations here. And so one of our equations is that this is our system curve, and then the other equation is that H pump is what we get from the pump curve. So two equations, two unknowns. H pump and Q. Okay, two equations and two unknowns. So we can calculate, so delta Z and then this whole thing here are A and B. We can get those. So we have A is 20 meters. We know that one right away. And then B we have is 8FL over pi squared G D to the fifth. And so 8 times 0.02 times 1,000 meters over pi squared, 9.81 meters per second squared, and 0.3 meters to the fifth. And that should give me meters everywhere. So this is going to have units of time squared per length to the fifth, so that when it's multiplied by this, it gives me units of length. That comes out to be 680, and that is going to be second squared per meter to the fifth. So our system curve, which is the right-hand side of this equation, which corresponds to the friction losses, has to be equal to our pump curve. And remember that this pump is not a constant. Don't think of it that this is not the pump curve over here. This is the system curve. The pump curve is this tabulated value. So two equations and two unknowns. Okay, so H system is 20 plus 680 q squared. So here's one equation, equation 1, and then equation 2 is pump curve. Okay, two equations and two unknowns. All right, so if we can find the point where they intersect, that's one way you can solve a system of two equations and two unknowns, then we can calculate that. So what I'm going to do here is I'm going to make a table here of values. And again, if you had a computer program that you could use to fit this pump curve, then you could have it calculate that. But typically this is done graphically because the manufacturer of the pump is going to give you a curve. So what I'm going to do is I'm going to make a table here. I'm going to have H, and so I'm going to have Q first in meters cubed per second. Then I'm going to get H pump in meters, and then H system in meters. Okay, and so we have 0, 0.04, 0.08, 0.12, 0.16, 0.20, 0.24, and then we said this is 50, 48, 45, 40, 33, 23, and 10. So that's the pump curve, and now we have to calculate the system curve. So if Q is 0, here we get 20. That's our static head. And then if we plug in here 20 plus 680 times 0.04 squared, that is going to give us a value of 21.1. And then so on here, and it's the same thing with just 0.08 and so on. And so we're going to get, these values should be 24.4, 29.8, 37.4, 47.2, and 59.2. So you can kind of see here H system, the energy that it requires. So if I at 0.12 cubic meters per second, if water were moving through this pipeline at that speed, I would need 29.8 meters of head. Basically, that would be what would be consumed to go from here to there. So you'd lose 20 to go up, and then you'd lose 9.8 from the friction at that flow rate. If you go up to 0.16, then this jumps to 37.4. The pump, on the other hand, will only give me 40. Will give me 40 at 0.12, and then it drops down to 33. That's all I can get. Again, as the Q gets bigger, the amount of energy the pump will give me is smaller and smaller. But so you can see that right here, this goes from being smaller to bigger. So my operating point's somewhere in between those two flow rates, about 0.14. But you can determine this using just by plotting them on a graph if you want to be more precise. And again, often instead of the table, you'd be given just a pump curve. That's what they would do. So we're going to plot here our H in meters. This H is for both the system and the pump curve. And then here we're going to have Q in meters cubed per second. And so I'm going to make these increments of 5 meters. So this will be 0, 10, 20, 30, 40, 50, and then down here we're going 0, 0.04, 0.08, 0.12, 0.16, 0.20, 0.24. Okay, and so our pump curve here is 50 and 0, and then 48, and then 45, and then 40. Oh, I didn't I went one too far here, didn't I? Oh, goodness. 45, and then 40, and then 33, and then 23, and then 10. Okay, so those first couple I went one too far. That's why you never want to do this in pen. But here I am. Okay, this is our pump curve. This point here is what? The shutoff head. And now we need our system curve. So we have 20 at 0, and then 21.1, 24.4, just under the 25, 29.8, just under the 30, like really pretty much right at the 30, 37.4, okay, halfway between those two, 47.7, right there, and then 59.2, which would be up here somewhere. So that's our system curve. Okay. Our system curve. This is our static head. Okay, dynamic head changes with flow rate, and this represents the energy you need to move it through the pipeline, and the pump curve is the energy we get from the pump at those different flow rates. So we need to know if I turn this pump on, where's it going to be? And it's going to be right there. That is our operating point. And it looks like that's about 0.15. So if I'd have just guessed 0.14, I'd have been wrong. Meters cubed per second, and it looks like the head there, H pump equals H system. Remember, these are variables, they're not constants. We have to figure them out, and that's about 35. I think 30. I said it's 36 when I did this before, so it's maybe a little bit above that line. So 36 meters of head is what I'll get. That's what will be the energy losses at this flow rate. And yeah, other point here, so this is our run out. Remember, these are all the things that I said you need to know. So the run out here, where it runs out, once you get above a certain flow rate, it's going so fast you can't get any good pressure addition from this pump. Okay, so I think that's everything I wanted to label. And the last part of this question is, what is the power? So we have P is equal to gamma Q H over eta. And yeah, so we know Q and H, that's what we just figured out, and we know gamma from water. I should have written that down over here on the last page, I guess, but gamma is going to be 9.81 kilonewtons per meter cubed for water. And then eta we said is 80%, and that's going to be both the losses in the motor and in the fluid. So 9.81 kilonewtons per meter cubed times 0.15 meters cubed per second times 36 meters over 0.8. So remember, the eta has to be in the bottom here, because the less efficient it is, the more power we need. So this is the power input, brake horsepower. Units here, so this is kilonewtons per second, kilonewton meters per second, so that's a kilowatt is a kilowatt second. Let's see, per kilonewton meter, I believe that's right. So kilonewtons, yeah, and meters, that should all cancel out. So the input power that I need that comes out to be 63.7 kilowatts. So that's how much energy you would need to pump 0.15 cubic meters per second, and the head that the pump would be putting out is 36 meters, and that would also be the head that's lost as the water goes between the two reservoirs. So that's how you can use a pump curve and a system curve to analyze a pump to figure out what its flow rate will be. We'll pick up there next time.